Hey guys, this will be a video on friction and rocket problems just to help you review for those types of problems. I've got a reminder up here at the top that friction and rocket problems are very similar. In fact, I'm trying to explain that they are pretty much the exact same, just that friction is horizontal while rocket problems will be vertical. In both cases, you're dealing with opposing forces, either friction, slowing a box moving, or gravity, which slows down the rocket or the object that you're trying to move into the air. So in both cases, when you apply a force, you have to apply a force not only great enough to accelerate the box or the rocket, but enough force to overcome friction or gravity. That's what these equations up at the top here are trying to show. When you have this is talking about how much force it would take to get the box moving in a world where friction didn't exist. So if you have a 10 kilogram box and you want to move it at 10 meters per second squared, that would be 100 newtons of force. This is the amount of friction that's present. So if you add those two together, you come up to your total net force, how much force you have to provide that box in total in order to not only overcome friction, but also to get it accelerating at the rate that you would like. Same thing for the rocket here. If you have, you want to get that rocket moving at a certain rate of acceleration, that will take a certain amount of force. You also need to factor in gravity, and combined together, we add those two together, and it equals your net force, or your thrust. There should be an S in there. So we've got a couple practice problems, and they switch back and forth between friction problems and between rocket problems, so you can see exactly how similar they are. So in this first one, we've got a 5 kilogram box with 10 newtons of friction, and this is the rate at which you'd like it to accelerate, 10 meters per second per second. So I always suggest drawing these out. If this is your box, I usually write 5 kilograms right in here. And I like to move left to right, so here is my 10 newtons of friction. I would like it to move at 10 meters per second squared. So if we're first just going to figure out this piece, the force of the box moving, without friction being accounted for, that will be 5 kilograms times 10 meters per second. So 5 kg times 10 meters per second squared gets us 50 newtons. If there's also the 10 newtons of friction, we add that on, and we come up with our total net force, or the push that we have to give it, 60 newtons. So the push that you actually need to give the box has to be greater than your original force and has to be greater than friction. It has to be the combination of the two in order to actually get that object moving. If I only gave it 59 newtons of force, it would start moving, but it would not accelerate at 10 meters per second squared. You could actually calculate how fast it would move. In problem number 2 here, this is your basic rocket problem, and it's set up in the exact same way. We've got our 100 kilogram rocket, and we would like to accelerate it at 20 meters per second squared. Now in this case, you're not given the force of gravity like you are the friction. You have to solve for that. And the reason you have to solve for that is because since you know the mass, that's not a hard thing to do because we just multiply it by the acceleration due to gravity. So again, I draw this out. Here's my planet Earth. Here is my rocket, right? There are the wings, right? Great looking rocket that would not fly. And here's the flame. Always got to have fire. So we've got 100 kilograms, 100 kg. We want it to go up at 20 meters per second per second. So we just worry about the upwards motion for now. 20 times 100. 20, add 2 zeros, 2,000 newtons. Right? And then if we're dealing with the downward force of gravity, if force of gravity is equal to the mass times acceleration due to gravity, the mass being 100, acceleration due to gravity being 10, we come up with 1,000 newtons. So up here, we've got the force of the rocket plus the force of gravity to equal the net force. So therefore, 1,000 plus 2,000 equals 3,000 newtons of net force. That's the amount of force necessary to overcome gravity and to accelerate that object. So as you can see, we solved both of these in the exact same way. The force of this object here to accelerate it, 5 times 10, 50, added it to friction, came up with 60. Here, we did the same thing. We found the force necessary to accelerate this object. That's 2,000 newtons plus its weight or its force due to gravity, 3,000 newtons total to get that rocket moving. Right? So in both cases, we solved in the same order. Now, 3 and 4, we're solving kind of in the backwards order. You know the 50 newtons of force that you have. That is your push. That's right here. You're given this, and you're given the friction. So now we need to figure out this piece right here. Okay, we're just going to be working backwards in this equation. So we've got our 20 kilogram box, 20 kg. We've got a 50 newton force. We've got 5 newtons of friction. So in this case, we would subtract friction from the net push, from the net force there, because we want to know how much force will be left over after we overcome friction. Right? We're starting out with this variable here. We're going to subtract friction so that we can get the force of the box moving. So that would be 50 minus 5 newtons is going to give us 45 newtons. So that's how much force we have to accelerate this box. But we want to know what the actual rate of acceleration is. So if F equals m times a, 45 newtons equals 20 kg times acceleration. Divide both sides by 20. We cross that out. We are left with acceleration equals 22.5 meters per second squared. And that would be your answer. So in the same way, we're going to solve this next rocket problem. We've got a 50 kilogram rocket, 500 newtons of thrust. Remember, if we come back up here, thrust is the net force. Since we know the mass of the object, we can easily calculate its weight, its force due to gravity, subtract these two, and be left with the force of the rocket. And then we can solve for the acceleration once again. So, draw the picture. We've got our rocket. Right. Flame, of course, 500 newtons of thrust is what we are starting off with. That's the total amount of force that the rocket can produce. It's a 50 kg rocket. If it's a 50 kilogram rocket, we can easily calculate F of g, because that'll be 50 kg times 10 meters per second squared to account for gravity. Force of gravity, therefore, will equal 500 newtons. Uh-oh. What's going to happen here? If the thrust of this rocket is 500 newtons and the force of gravity is 500 newtons, 500 n minus 500 n is going to be 0 n, meaning there will be no force left over. Right? So that's what would happen. Same thing if you're left with friction. If you have as much friction as you do net force, if you do push, the object's not going to go anywhere. So for the sake of showing us how to actually solve all of this, let's pretend for a moment that it's actually 600 newtons. Right? I just wanted to go over what would happen if the thrust was equal to the weight. Right? So if we have 600 newtons of force, we made some modifications to the rocket. It's a little bit stronger. It can now produce 600 newtons of force. How would we solve it? How would we find the acceleration? Coming back up here, we've got our net force, that's 600 newtons. We've got the force of gravity, that's 100 newtons. If we subtract that, we'll get our force of rocket. So, 600 newtons minus 500 newtons equals 100 newtons of force to accelerate that rocket after we've dealt with gravity. Being a 50 kilogram rocket, we can figure that out. 100 n is equal to 50 kg times a. Divide both sides by 50. and we are left with A equals 2 meters per second squared. So in all of these cases, it revolves around this concept up here. Now, these are not real equations, right? They're not, just like F equals M times A. They're not something that you can necessarily just plug numbers into. These equations are really trying to explain some concepts to you. If we have the force that it would take to get the box moving without friction, we added it to that unfortunate factor of friction, we would figure out how much force we have to actually push the box with. Same thing for the rocket, right? We have to take into account the force of gravity, the object's weight, as well as the force it would take just to accelerate that rocket, and that will be our total force in this equation. So in both cases, we want to understand that what we're talking about here are opposing forces. The force of the rocket and the force of gravity are two opposing forces. So if you still want that object to accelerate in spite of gravity, you need to give it more force. If you want that box to move in spite of friction, you're going to have to increase the push, the net force that you give that box so that it starts moving. The best way to do these problems is first to understand what these equations mean. As soon as you understand it conceptually, then you can solve it using the pictures or use your, do it in your head. You can visualize this. But until you understand these concepts, it'll be much more difficult. So if you're confused about these pieces up here, come and talk to me.